Welcome to Fantastic Plastics, Strategies and Techniques for Injection Molded Part Design. My name is Andrew Lowe. I'm a senior industrial designer with the Damani Group. The Damani Group is a small product development consultancy located in the Chicago suburbs, about an hour or half hour west of downtown. A little bit about myself. Like I said, senior industrial designer of the Damani Group, collector of mid-century design, builder of custom coffee tables, and now a 6-time SolidWorks World presenter. In the past, I've focused on surfacing kind of presentations, but changing into more solids, plastic part design for this year's session. Also, shameless self-promotion. I build custom coffee tables, wood, metal, functional art. We combine the warmth and natural look of live edge slabs with precision engineered, meaning I can't weld, so we do them 60-61 on the Bridgeport mill and bolt them all together. And why should you listen to me? I've worked on numerous projects with complicated plastic parts and assembly sequences. How are we going to put all those different plastic parts onto a machine in different directions and such? Damani Group, we often get hired on a project or brought in to help out clients of ours to solve the really tough design problems. This was a series of slot machines we developed for WMS Gaming a couple years ago. But lots of plastic parts, lots of assembly sequences, complicated geometries, got to go all together. And what we'll cover today. So today we're going to look at workflows and modeling strategies that I personally use to quickly and efficiently model plastic parts in SolidWorks. And as with everything in SolidWorks, there's a multitude of ways to do the exact same thing of creating geometry. So the concepts that I'm going to present today are the way I do things. If you do have another workflow that works great for you, I'm not trying to say that mine is better than yours. They're just different. And that's the nature of the beast with SolidWorks. There's so many ways to do the exact same thing. And the one caveat is this session assumes an understanding of injection mold part designs, guidelines, and best practices. We need to have draft, nominal or constant nominal wall sections, et cetera, et cetera. I will not really be getting into the nitty-gritty design aspects of injection mold plastics. If you are looking to cover that, check out this free GE design guideline. I had a PDF. I found it years ago, and I've got it in a folder on my desktop. I'll put it online on our company website. One thing to note is when I present, I try and go pretty quick and jam a whole bunch of content in, so if you don't necessarily get everything written down, we will be putting the entire PowerPoint online on our website. Grab a business card with our company address at the end of the meeting. All I ask is if you take a business card, leave a business card. And with that, let's jump into the content. We need to start looking at a master model workflow, and this is a lot of the time we'll work with our clients for developing plastic parts in that their internal design department, their ID guys, they come in and they've developed all the aesthetic surfaces of the model, but maybe they haven't figured out any of the attachment details, any of the internal geometry that may be required to have these parts functionally work. But we want to maintain those models. We don't necessarily want to remodel everything. We want to get them into SolidWorks. So master model workflow, I'm sure everyone is familiar with it. We have one body or one part with all the bodies, and then we split the sub-bodies out. There's just many different ways of splitting out the sub-bodies, but I think there's only one right way of splitting out the sub-bodies, and that is using the insert part feature. So insert part's great, insert, and then it's actually insert part, and now it'll bring all the geometry from your parent part into the child part, but you also look at all this extra geometry you get. You get solid bodies, you can bring in surface bodies, axis planes, absorbed, unabsorbed sketches. All this you can bring in from the master model. Using the save bodies command, you can bring in bodies, but you don't get any of that other stuff. As well, if you do sheet metal, you can bring in the sheet metal information right here, and it'll actually bring in the flat pattern. This is a great way of doing mirror sheet metal parts. Insert mirror part, bring it in, bring in the sheet metal information, and you've already got the flat pattern and the bends and such in your mirror part. One thing to consider when working with master models is it's always going to be looking out to that parent part for those references, unless we look at locking them, which is going to save us some rebuild time. So here in SolidWorks, this is the completed master model. Here we've got 4 solid bodies. I always have my solid and surface bodies folders shown by default. And then, so what I've done is, when SolidWorks decides to give me my mouse back, I'm going to roll up. So in 2015, I believe, they introduced a new feature, body delete keep. So before you could always delete a body, but now you can just pick the body you would like to have kept. So I'm just keeping the one body that I'm going to add all my internal features. You can see it's just an empty shell right now. And here's the insert part feature, and it's currently out of context. To bring it back into context, we can edit the feature. So you just right-click, edit, click the checkbox. It's going to go out, get the most recent version of the geometry. And here we had a rebuild error because I've been playing around with all of this stuff, and just to hide some of this stuff, all the bodies are mixed up. But in general practice, it's not going to happen to you. But locking those external references, I'm going to right-click my master part, list my external references so I can see everything that's going on, and I'm going to hit that Lock All button. So what this is going to do is going to lock them. It's not going to reach out and look for those references, but it's not going to have to rebuild. Otherwise, if I went and edited this part in the assembly, or maybe jump back to an assembly, it might say, oh, I wonder if it's changed, and it's going to do a rebuild of all of the features in the master part. So by locking it, I save myself that rebuild time, and then when I do actually need to rebuild it, because there maybe have been some edits to the master model, I'll unlock them. One thing I never do, and I potentially run into some situations where PDM software requires this, like third-party, not SolidWorks PDM system, is break the references. Because once they're gone, you never get them back. So the break is a one-way, and you also get a big X in your tree here, and you can never get rid of the X in it. You know, who likes a big X on the top of the tree? That's my recommendation, would be locking those external references, not breaking them, to save yourself the rebuild time. Having access to the master model is great. If you were to break the references, there's a lot of things it's more useful to actually do and roll back. For example, creating screw pockets. It's far easier to add them in the master model than it is to try and detail them in the child parts. Likewise, a lot of industrial design models we get in, they have little 5,000ths or 10,000ths fillets on all the edges because it looks nice on a rendering, but you can't add draft to a filleted edge. But if you can go back into the master model, roll up before the shell, roll up before the draft, it's really easy to add draft to missing faces. So working with draft, it's a plastic part. We know it's got to have draft. We all know what core cavity we need to have. We should all know the analysis tools, the undercut and the draft analysis tool. And the first thing I do when I get a model in, especially if it's come from an industrial design department, I want to verify the outside draft. This part was actually pretty good. The customer kind of knew what they were doing. There's actually a little bit of missing draft right here, which we'll look at addressing in a second. These faces actually have less than the required texture. I think it was 3.5 degrees on this part for 11030, and these were probably 11010. So that's why they're yellow in this. But I need to know how much work is going to be required. Can I work with the original model, or am I going to be hacking it apart to try and get draft in the model? How much work is it going to be to add all of the draft to the various faces? So if we were to go and add missing draft to ruled faces, it's pretty easy. We open up the part. We can apply a parting line draft feature using the pull direction plane. And by rolling that model back or having access to the master model, you can easily add the draft there and then get it on both sides of the shell. But if I was working with imported geometry and I have all these fillets here, then I'm going to be needing to use the delete face tool and try and blow away all these fillets so I can get a sharp edge so I can go and apply the draft, because there's no way I'd be able to draft this face where my mouse is having all of these fillets on this edge. So whenever you can, try and get access to the original geometry, just so that way you have the power of rolling back. But if you are stuck working with imported geometry, then delete face and a whole bunch of clicks and try and blow those fillets out so you can add draft to the edge. Drafting arced faces. So these are faces kind of created by a revolve feature. We know that a revolve is a perfect circle, and a perfect circle has 0 draft at the horizon line. But there is a way we can quickly add draft after the fact to these this kind of geometry in SolidWorks. So this is a portion of a housing that actually goes in a sump pit. And so if we turn on the draft analysis, note that I'm using the default planes wherever possible. And this is the bug in SolidWorks that keeps biting me, that if you pre-select a plane, it does not work for draft analysis, but regardless. So here we can see the yellow, the missing draft, close to the parting line. This is actually going to be split in half. It's going to be 2 halves of a housing. And I'm going to use the split line tool and a different incarnation of it than we may normally be used to. So this one's already generated just to show you what this looks like. So I'm going to use a silhouette split line. So what this is going to do is kind of find the silhouette edge with my desired draft angle, which is 3 degrees here, and it's going to introduce a new edge on my model right there at the 3 degree mark. So now I know where 3 degrees hits. So I'm just going to delete this split line surface cut for symmetry because I'm lazy and only like doing as much work as required, and picking twice as many edges and faces, not for me. So here I'm going to pick the edges that I've split with the silhouette split tool. If we exit out of the draft analysis, one thing to note, these little yellow arrows show the face that this is pointing to. We need to flip this. Usually the default is wrong, so if I get other face and I find a little yellow error and I go arrow. Now we have, when evaluating our draft, correct 3 degrees. But note that I'm always adding material because I need to generate that new edge. So this is originally where this face was, and now I've introduced a small kind of flat on the model, and this is perfect 3 degrees. So we will now have correct 3 degrees for the texture on the part. We're not going to experience any drag or anything when the part's ejected from the tool. And I've quickly added draft to geometry. So if you're working with imported geometry and doesn't have quite enough draft at the parting line, the split line silhouette trick, parting line draft, guaranteed to get you the correct result. You may just need to do it for both the cavity and the core faces. So here we see the example, the silhouette option. You can't change it after the fact, so you have to generate a new split line, have that silhouette option on, and your required draft or desired draft angle. And we're using the parting line draft. Be aware of those little yellow arrows and make sure they're going on the right way. One other thing to consider is actually building draft into cylinders. So a lot of time, I keep a little sketch like this on my desktop. And I just copy it in a new sketch. But what I do for actually creating circular geometry that has the correct draft, so I'll dimension this circle. I'm going to throw a center line across here, and then another center line for symmetry. And I'm going to set this to construction. So this circle will drive the size of my drafted circle. And to exaggerate this, I use the little auto transition, and then we'll go tangent. And we'll add that on. So you can kind of see what I'm doing here. I'm actually building that little flat in. And the benefit of this strategy is that by building the flat in, we control the exact dimension at the parting line versus adding material. Now, I didn't actually add much material. I think I measured it, and it was 1.4 thousandths of an inch, so it wasn't much. And there we are, fully defined. And if we zoom in here, you can see that we're slightly deviating from a true perfect circle, but we have correct 3 degrees draft. Oh, no, that's my 3. Oh, why are you all the way up there? One thing that doesn't work, if you need a really ridiculous draft angle, like 15 degrees, you may want to start trying something different, like a spline to approximate a circle, just because the amount of deviation that you see here. But useful little technique for building in draft to circles. So correcting the surface geometry I showed in the last slide. So here we're seeing the zoom in. We're actually down to about 1.5 degrees through this yellow portion when this part needs 3.5 degrees of draft. And the designer was very well intentioned. He actually deliberately tried to build surface draft into his surface models. But we needed a little more help in the surface model to get exactly the correct draft at the parting line that we were looking for. So going on to our next example. So what he had done here, if we look at his original surface versus what we corrected it to. So if I actually show this, what he did was he set all of his arcs that make this kind of crown face, he set them all to be tangent to center lines with the 3 degree draft angle. So all of his profiles are good. Every time there's a profile in his loft or boundary surface, they're very similar. He has the correct 3.5 degrees draft. Where the draft is not correct on this part is through here, because there's nothing shaping what this surface should look like other than these profiles here. So we need to give a little more shape to this surface to correct it. And I didn't actually have to rework. I didn't have to build a new surface. I was able to use the existing surface by giving a little more information to SolidWorks. So I'm going to roll back up, and we're going to take a look at our draft analysis here. We'll pick this and the right plane, and actually 3.5. We're missing a little bit down here, and I know that's on purpose. It's kind of hard to explain why it is, but it gets cut away anyway, so I didn't bother trying to correct it. But here, correct draft. So how did I get that? So one thing I've actually done to make this easier is I turned on the flat display, tree display, show flat tree view. So nothing gets absorbed because there's a whole bunch of sketches that make this loft, so you can kind of see them in the tree. So what I did was I rolled back and I found the original sketch that he had used to define kind of where the parting line, the outside perimeter of this part. And I created a new surface extrude feature. And I gave it draft in the feature. So now my surface extrude is actually kicking away from the parting line at the correct 3.5 degrees. And what I can do with my resultant surface is I went back in and I added a little more intelligence to this sketch by using a little known sketch relation that I'm going to show you. So if you pick a sketch entity, the edge, I need to turn on my selection filter to get the edge, and the face, I have a new relation, tangent face, so I can actually make sketch geometry tangent to surfaces or solids for whatever reason, but if you need to make a sketch entity tangent to a face, you can do that. So I add the tangent face to this. Now, whenever I update this surface, maybe it goes 4 degrees, I end up getting the correct, the arc updates because of that tangent face relation. So these are the additional curves required to make this shape. So all I had to do was change the original definition of this surface from, instead of being just using that sketch, I used an open group, so I used the selection manager, right-click selection manager, picked the edges of that draft surface along the parting line, and I made the tangency to face relation. So with none, right now there's nothing guiding the shape of this surface other than how it flows from here to here to here. It just has to follow this curve. By putting tangency to face option on, now I'm telling SolidWorks, no, hey, this surface has to be tangent along this entire perimeter, and because that surface is at 3.5 degrees draft, our main surface is inherently at 3.5 degrees draft. One thing to also check out is this little tangent influence. If you turn on the curvature display, the curvature combs, so this is actually kind of what the surface is doing in terms of how the rate of change of the curvature of the surface, and I want density with the tangent influence down. Take a look at the blue ones on the screen, especially down here. It's actually, this is an inflection, so it's changing direction on itself, and this technically would be an undercut because of how it's inflecting like that. So by using that tangent influence, I say to SolidWorks, no, get all, the majority of this surface shape should be taken from this draft reference surface. And if we were to evaluate, we're at 3.5 degrees. So I didn't actually have to rework this. All I needed to do was add a new surface and then set the original surface to be tangent to that, corrected all the draft issues that this part had. So here's that surface extrude. Make sure that you have the desired degree of draft here. And here we're correcting the boundary surface. And there's that neat little trick, the tangent face. And if you are interested in that kind of modeling, check out my presentation from SolidWorks 2015, where I spend 90 minutes on surface modeling with draft. It's on YouTube. It was either broken out sections, or you can watch the whole 90-minute video. So moving on, now that we've corrected the draft issues on this part, we've got to get a lip and groove into this guy. Well, not into this guy, but into a part in general. And I go about a particularly unique way. I haven't seen that many people doing lip and grooves this way. So I don't even try, well, I've seen them done lots of this way. So I don't try to build the lip into, or the groove entirely into the nominal wall. I set up these little fingers along the perimeter, and they act as the stop so the parts are interlocked. But I create all of my lip and grooves, whether it be planar or non-planar, with the thin feature extrude or thin feature cut extrude tool. And I hope that you see the benefit of why I go about that way. So I know SolidWorks has that parting or lip and groove tool, but it only works if both of your bodies are in the same part. And I try to do all the detailing of these parts in the children just because I want to keep all the overhead of all these detailing features that industrial design might not care about, the engineers do. I want to keep them in this child part so that way I'm not paying for the rebuild of all the screw bosses and the ribs of 4 bodies in that master part. So I'm speeding up my workflow by breaking this up. The other benefit of this is that once the models are split up, I can assign design tasks to other open resources in the office and say, hey, here's this part. Can you add some ribs to it? Can you fill it some of the intersections? Can you add a screw boss here? If they were all in one model, only one guy could be working on it, so we can speed up our design time by having multiple people work on the child parts. So we're going to take a look actually how I pattern the fingers a little later in this presentation. But now take a look at how we set up this cut. So the order of operations is a little bit important here. Before I created the groove, I already had these fingers. Like I said, we'll talk about how I generated them later. So I start a sketch on this plane. But you'll note that because these fingers are here, now I have to pick all of these segments, and they're not continuous with each other. They're a little disjoint. So I'm just aware of the order of operations. So I just roll up. And then I actually put the sketch for my groove, and I usually always pick the inside edge, and I try to avoid sketch offsets wherever possible. Right-click, select tangency, grab that whole loop, convert entities. I've got it in my sketch. The reason I avoid offsets in a sketch is that, especially with splines, they're really unstable. If stuff changes, there's no way to reattach an offset sketch relation. So if it goes dangling, you can try and delete the references, and maybe you'll get it back, but odds are you're going to have to delete your entire offset, re-offset it, put it back together. But with the thin feature extrude, I'm getting the other half of my lip and groove automatically. So here I set up 2 direction. I've got my lip going a little bit into the fingers here, and then we're also passing through into the main body. I am a huge advocate of adding draft to the features wherever possible. Sometimes you can't, and you have to go back and add parting line draft. But here, I save myself clicking all of these edges by building the draft into this feature, half degree. If we were to maybe put this up to 5, you can see kind of this exaggerated. Just make sure you've got the right draft outward or draft inward going on so you're not creating undercuts. You want the draft going the right way. But super simple way to do planar lip and grooves is just convert that whole chain of edges into a sketch and thin feature extrude cut, and you can control the entire size of the groove with one feature. And so planar lips work the same way. I still am an advocate of the thin feature, one direction or 2 directions. That way I'm controlling the offset in the feature. One thing you may need to do is use a replace face on this end to clean it up, so that way the end face of the lip is the same face as the rest of the part here. So we took a look at a planar groove, and now we're going to make a non-planar lip. So I'm still going to use the thin feature extrude tool, but it's going to work a little bit different. It's going to be some more steps, but I'm going to get a non-planar lip when I'm done. So let's roll back up and take a look at this feature. So here the body's shelled. This part was already asymmetric, I think, for, I don't know, whatever reason. But it's the bottom of a mouse, and it was just a good example to create a non-planar lip on. So I have to do the entire thing. So the first thing I do is create a new plane parallel to the pull direction of the part. You'll always want to be parallel to the pull direction of the part when doing the non-planar lip and groove, so the thin feature works correctly, and you can draft it correctly and not get any undercuts on the part. So I now need to create a surface that will drive the top height of my lip. So here I've used the surface offset tool just at 100 thousandths. And then I love this tool, untrim. So I just pick those faces. I set 0. You don't really set a distance, it's just to present. So this is just basically going to erase the cut that was in here. So it's just going to make this one big large surface again. So now I have the top height of my lip. And so what I've done, if we expand this feature, take a look at this sketch. So all I've done, the exact same example, just from that plane parallel to the pull direction, I've converted the inside edge of the part. And now I'll use a thin feature extrude, just like I did before with the groove, to add the geometry back into the part. And now you can kind of see where I'm going with this. That offset surface is now used for a surface cut, and I've now cut the non-planar lip to size. So this is kind of a bad example because I also could have cut it like this, but if it was also non-planar in this direction too, I couldn't use just a cut in one orientation. I do need to have that surface. But you can build some really complicated lip and groove geometry really easily by just remembering that you've got your thin feature extrude that actually creates the geometry, and then the surface cut that either defines the top of the lip or the bottom of the groove. The last thing we need to do is add draft to this part. Because this is non-planar, I can't draft it in the first feature because otherwise the lip would be different thicknesses all the way through its perimeter as the draft would have been applied from the original extrusion plane. So here, this is kind of one of those things that it just sucks and you've got to pick and click. There's some ways to speed things up, like right-click, select tangency is going to get you a bunch of them. Same over here. This is just a downside of doing non-planar lip and grooves. But this method, by using the thin feature extrude solid geometry, it's a lot easier than other methods I've seen with offsets or surface offsets, extends, trims, sweeps. The sweep can be dangerous because the sweep can introduce undercuts as it sweeps along the perimeter. The thin feature extrude in the direction of the pull direction always going to get you a nice, clean, uniform thickness lip and groove. You just got to come back and use that parting line draft tool at the end to add draft to all the faces. So here's that plane. You can see, just make sure it's parallel to pull direction and you won't have any issues. Surface offset and the untrim to get our cutting surface, whether we're cutting with it or we're using an extrude cut up to it in the case of a groove. And then using the surface cut to remove the material, and then coming back and finishing up with the parting line draft tool along all of the perimeter edges, which is the most painful part of the process, but it doesn't take that long. And if you have an intern, maybe you can make him click everything. So now we've got a lip and groove. The parts are nicely interlocked. Take a look at how we might put them together, some screw bosses and some screw pockets. Screw pockets are super easy if this is housing. Oh, I picked the mirror face, so it's going to think for a while. We want the non-mirror face, so I can roll up before the screw pocket. Screw pockets, all I do to create a screw pocket is just create a cut before the shell. So cut the pocket with an extrude, draft it or build the draft in. And there was some additional detailing, shell it. And now on the opposite side, you always get the screw pocket. If you want to make it a little thinner, save a little bit of material. Instead of being the nominal wall, you can use the multi-thickness shell tool option here and just set a little bit. So note that it's not a global multi-thickness. You need to pick each of the faces individually and multi-thickness. But surefire way to always add screw pockets if you have access before the shell. If the part's already shelled, can't do that. Plan B, which is a little more work, but we're going to do it with the intersect tool. So here this part's shelled. Now, I know you might be saying he's got the shell feature, why not roll? For the sake of this example, let's ignore that. I'm actually going to model the interior volume of the pocket as an extrude, because I can't cut. I don't have any geometry there to cut before the shell. So this is actually, think of this as the cut. This is the negative space of the screw pocket. And then I'm going to shell each one of them individually, but I pick shell outward. So now what was my negative space is actually the negative space. So I'm using a solid to essentially cut what's not there. Because I have two screw pockets, I've got to shell each one individually. And then I used the new intersect tool. This was 2014, I think this came out in 2013. Not entirely certain. I pick the bodies that I want. We'll just demo this. So I'm going to grab this. We're going to intersect. And now what I do is I pick the stuff I don't want, and you can see that the graphics preview goes away. So you just pick the stuff you don't want, and click OK. You're good to go. If it was easier for you to pick the stuff you actually want, because there's a whole bunch, you can just pick stuff that you do want to keep, even though it says region to exclude, and then invert selection, and then it gives you all the stuff you want. Finally, I'm going to clean up the sharp edge here. Oh, I added the through hole. And whenever I'm working with non-planar intersections, so if the edge is on a bit of an angle like this, which on screw pockets and consumer goods, often the case, I use a face fillet. The reason I use a face fillet is because it's got this awesome chord width option. So it's symmetric fillet. You can see how the fillet gets large over here and is smaller over here. Designers love fillets that look the same size, even though the radius is changing along their perimeter. So change that chord width, and now it's visually the same size, and I've finished off this screw pocket. So if you don't have access to the original master model, not a problem. Just model your screw pockets, shell them, and then use the intersect to put the geometry back together. So here we see using a cut before the shell to create the screw pocket. And then if you can't model it, we'll just model the interior volume, shell outward, intersect, and then remember that little chord width face fillet option, put it in your arsenal. One thing to be said, you can only add one chord width face fillet at a time. So this is a fillet feature, this is a fillet feature. Now we're looking at the mating boss. So we want to have a boss on the opposite half plastic to go in. And a lot of the time, based on the actual boss sizes, the boss is going to get thick down here. We're going to see some sink on the cosmetic face. So one little strategy I've done is use this indented boss, and I've seen them used a couple different times, but not everywhere. So I actually push the core pin a little bit farther down, usually about 40% or so of the nominal wall to thin this out, and then I add this little divot cut through here. And then I'll also come in with some additional ribbing to help the material flow. This is not pictured in this section view for the ease of clarity. These are really easy to create on planar parts. They're a little trickier on surface parts. I'm just going to show the planar part example. Let's take a look. Where are you, screw boss example? I don't know why these are out of order when SolidWorks. There we go. Screw boss example. So roll to the back side. Take a look. This is just a revolved cut. One thing to note about the sketch, try and build as much parametrics into my model wherever possible. So I used a center line, and I pierced it to the top of the boss, and I pierced it to the bottom of the boss. Automatically figured out the draft angle of that boss, right? Because as the edges move, if there was an update. And then my little sketch here. So here I'm going down 40 thousandths, 40% of the nominal wall. Added this line collinear here, a little bit of a fillet on the bottom. And I see these details at between 15 degrees and 20 degrees. What this is going to do is just limit the material you've got going on. You're going to have a little bit less of a thick section where that boss hits your main face, and you're going to limit the potential for sink on the cosmetic face of the part right here as this part cools and the plastic wants to shrink away. And then later on, come back and add some ribs just to tie this boss into the main wall of the part. So a nice little thing to put in your arsenal. Design binder. I love the design binder for working with plastic parts that have little inserts and things in them, and I want to make sure that I get the dimensions right. So here I have an insert. It's a Dodge UltraCert 2. So I went to the Stanley Engineering website, and I looked up the data sheet for this little insert. And I wanted to make sure that the data sheet for the insert traveled with it. So the design binder is not on by default, but you can go, I think it's Options, Feature Manager, and turn it on by default to always show. And I use the Windows snipping tool. And I just grabbed this little screenshot from their website, and now I stuck it in the model, and I can always go back and reference to make sure that I had the hole size for this insert, that I had the little 8-degree lead-in that it required correct. Gives me a little bit of information here. So if you ever have a data sheet that you want to have travel with the part, throw it in the design binder, you're good to go. And now whenever I want to reuse this insert, note the next thing I did, any guesses where this part came from? McMaster Car. What do I do to McMaster Car parts? I love them. But they have all the little knurling and the threads. Plastite screws. Here we go. We've got a plastite screw. So the very first thing I do when I download this from McMaster, they're usually always a cut sweep. Find that cut sweep, Suppress. Now the threads are gone from the model. I'm going to save a bunch of assembly rebuild time, more performance. Helical faces are very taxing on SolidWorks, so I want to get rid of those threads as soon as possible.
Is the design binder a link or an attachment?
You can do. The question was for the video: is the design binder a link or attachment? It can be both. So you have a Microsoft Word file in there by default, but you can throw in a PDF, you can throw in an image, you can throw in whatever. I find it really easy to just open up the Word document that's really already there, throw in a screenshot, and call it a day. And design binder's been around forever, but just little known thing in SolidWorks. So throw the data sheet in the design binder, suppress the threads on the fasteners and the inserts and all that extra junk that we don't want to have that slows down SolidWorks. So leveraging patterns. Like I said before, with the mirror example, I like to do as least a little work as possible, kind of lazy. It also just means I have more time to do other design stuff. So I try and leverage patterns wherever possible, and we're going to look at two different patterns that I think are uniquely suited to plastic part design and not necessarily machine design or sheet metal design, and that's the curve-driven pattern and the sketch-driven pattern. So the curve-driven pattern I use a lot to get these kind of finger shapes that make my lip and grooves around the perimeter of parts. And then the sketch pattern is great for placing instances of repetitive geometry around my part. So how does that curve-driven pattern work? We're going to take a look at that example. That's curve-driven pattern. Where are you? We're going to reuse this example. So this is the example we had the groove in. And so the first thing I'm doing is creating the rib. This is just, once again, a thin feature extrude. Use a ton of thin feature extrudes in plastic parts because I can define the thickness in the feature, and all I have to do is sketch a line. And I like to always use midplane, and now I don't have to sketch a rectangle or square or whatever. I can just use the thin feature. And the up-to-body option. I use up-to-body all the time because sometimes the rib is hitting multiple different faces along the model, so I can't just pick one. By using up-to-body, I know that the feature is going to terminate correctly at the main wall of my part, and I'm not going to get a situation where it doesn't go quite far enough into the part. Maybe there's a hidden undercut, something like that. Up-to-body, guaranteed to work well when adding little rib details and such to plastic parts. Once again, building that draft into the feature because I don't want to have to pick 25 of these little grooves times 4 edges, so 100 plus edges with the draft tool. So I'm building it into the feature to save me some work. I've got a little fillet just to break the sharp edge. And the curve-driven pattern. So what the curve-driven pattern needs to work is a sketch or a comp curve. So comp curve, you can just, what it does is it just puts together a selection of edges and then puts them into this new curve feature. So I couldn't actually pick those individual edges in the curve-driven pattern. I could if I just wanted to pattern along one edge, but I want the entire chain of edges in one go, one pattern. So that's where that comp curve comes into play. Now I'm using that curve-driven pattern. So my direction is the curve. Setting the number of instances, and there's a couple things to note about the curve method and the tangent to curve option. It's kind of easier if I just zoom in to show you what happens with these previews, and the yellow is coming across nicely on the video. So transform curve, it's not so obvious in this section, but over here you can see it's kind of guessing of where to put the instance. I'm not really certain what transform does versus offset, but this instance is now off the side of the part. Offset curve, right where that instant should be. The next one is tangent to curve, means that it will be normal to the face here and here and here. If I align to seed, all of the instances are kind of parallel with my original one. So this might have some options in certain situations, but for doing these kind of finger details, tangent to curve, offset curves, features and faces, I've just grabbed the fillet, because I don't want to have to fillet 25 edges, so that's getting patterned, and the groove rib. One thing to note when working with patterns and mirrors on plastic parts when patterning the features is that the draft feature does not pattern 100% of the time unless they fixed it. So you can actually add the draft, so we'll add, not the draft, analysis. Sometimes I mix those up. So we're going to add a 1/2 degree of draft to this feature, so 4 edges. And remember, I built it in, make sure we're going the right direction. Yep, we're on core side. And we'll turn the draft off of this guy. And now we're going to edit our pattern, because we want to try and pattern the draft, right? Pick the draft. Note that it let me pick it. Not a problem. I have to pick it from the tree. I can't pick it from the faces. Pattern rebuilds. Right plane. Draft analysis. 0.5. Ooh, what do we have here? This instance, half degree. No draft. So SolidWorks let me pattern the feature. No rebuild error. No pattern error. Draft does not pattern. But you don't know about it. That's why I always try and build the draft into this feature, because I know that draft doesn't pattern. I would need to pick all of these edges individually. One workaround for that is what we're going to look at in our sketch-driven pattern. So when working with the curve-driven pattern, just remember those 2 little options, the offset curve, tangent curve, and use our comp curve to give direction to the pattern. And it saves generating all that geometry by hand. Sketch-driven pattern. So I have sketch-driven pattern, and in this little screenshot, you'll see different colors. The reason I have different colors is because I'm using a multi-body approach. I'm going to model the little detail as a separate body, and then I will pattern the body with the draft already built into it, so I know that the draft will pattern. So here is the completed little snap hook. We're going to roll up. So my first feature I'm using to create the tab that comes off the part. I don't know why SolidWorks thinks to rebuild on this, but give it a second. So here in this sketch, I've actually put all of the dimensions that locate these 3 little tabs. Note that they are not really linear, so a linear pattern would not work well for this. And then the ones I'm going to pattern, I set as construction geometry. The reason I do this is we use model items on our drawings a lot, so we'll bring the model item dimensions in from the sketches instead of using just the driven dimensions at a drawing level. So I want to have all the dimensions even though I'm not creating the geometry. So I've created my first little tab here, and then just some additional solid modeling, pretty simple stuff. Added the hook, then the ribs. And one thing to note, right, we don't have an edge here. This face is bigger, so I'm not merging this in. I've got my little merge result button off. And then I just need to be cognizant when I'm adding the additional features that under the feature scope, I'm picking the appropriate body. I do not want to have this detail merge in. Here, I am trying wherever possible to pierce my geometry through the main wall of the part. Instead of just going up the surface, I would go offset from surface by a little bit, a millimeter, 40 thousandths, a third of the nominal wall. Then I had added some additional detailing. I added all the draft to this guy for both the lifter that forms the underside, plus the main open-shut action here. And if we look at the front plane of this part, once again, I get bit by SolidWorks' inability to pre-select draft. We've got the correct draft, and then the lifter's forming the other underside of this guy. And when I go to create my pattern sketch, we're going to be able to quickly pattern this body around the part. So I'm a huge proponent of showing my original sketches wherever possible and making relations to those sketches and not to the geometry. So I started a new 3D sketch, and I just added a sketch point in the center of where I wanted these instances. One thing to note, you need to have a corresponding sketch point in the exact same position. So it's kind of hard to see maybe, but there is a sketch point in the middle of this bottom line segment where my mouse is. And the reason being is that the way the sketch pattern works is it has 2 options to determine the placement of the new instances. So sketch pattern is going to generate either features or bodies. It works for both. Here we're using bodies and not features. Either at the selected point or the centroid. So if you use the centroid, these are not actually in a row like I want them to be. So they are not aligned. So centroid, I believe, is just kind of picking the center of mass of that body and saying, oh, this is the point we should mirror from. Or not mirror, but pattern. Here, I've gone in, and because my sketch is shown, I'm going to pick that corresponding middle point from my first instance, and now they're all aligned because the points are in the exact same position. I can't merge them in. That's where the combine tool comes in. So with combine, I pick all of my solid bodies, put them all together, and this is a surefire way to always be able to pattern draft in a part. Remember, and I can't stress this enough, and we've reported it for years to SolidWorks that we think it's a bug, that patterned draft does not pattern. It does not mirror the feature itself. Body geometry always correctly patterns because we've applied the draft to an individual body, and we're just patterning that geometry, not the features, which are the instructions the SolidWorks uses to actually create the draft on those faces. And that's just where a huge, or not huge, but why draft analysis is just so important when designing plastic parts, and just always be checking your work, going in, making sure that we've got correct draft everywhere. So sketch-driven pattern, really awesome wherever you have geometry that's not in a row, but you want to create a bunch of instances of it. Just remember that sketch point in the initial instance kind of lines up in the same position of the new instances, and turn off that centroid, turn on selected point, and you'll be good to go for patterning your body and then putting it back together with the combine feature. Oh, now we took a look at a multi-body strategy, but that was a workaround to get a pattern to pattern correctly. Here I want to look at multi-body strategies for actually creating more complex geometry on the insides of parts. This detail here is hidden by the corresponding part that comes over. There's some little press-in grommets here that screws go into. But this is all technically main wall section, so it should be built in before the shell. We don't want to build all these details into the master model because this is the engineering detailing. So we're going to use a multi-body strategy and approach that will allow us to quickly detail out that area of the part. Multi-body. Here's a completed detail. I'm going to roll up. And the first thing I needed to do when creating this detail is, actually, let's roll to the end again. If we look at this detail from the side, the other part has to nestle over top of this, and there were some clearance purposes. But if we look at the side, it's actually arcing and it's angling, so I needed to create this face at a corresponding offset to ensure clearance for the corresponding part that's coming in over the top and kind of meeting along this reveal joint. So the way I did that was I used the offset tool to get my clearance, but the offset wasn't quite big enough. So we needed to actually add material to our surface offset. And that's where surface untrim comes in. So we used untrim before to reveal the original sides of the surface for creating our non-planar lip. But this untrim example, I can actually make surfaces bigger by increasing this percentage. It's got a distance icon on it, but it's just a percent. And the percent really doesn't mean anything. It's kind of a crapshoot of what you get. So 100 could be really big on some parts, and it could be next to nothing on some untrims. But I'm just using untrim to add a little bit more. So untrim's different than surface extend. Surface extend uses an algorithm to mathematically figure out where that surface might be in the future, or not future, but farther along in space. Untrim, what it does is it reveals the original information of this surface. If we had looked at the master model, this surface here was actually much bigger. You can see the corresponding line. It went up to here. So I'm revealing original information that was in the surface but was cut away when this part was split into its 4 component bodies and then put into new parts. So I've got my offsets. I've got my untrims. And now I can use the trim tool. So I'm using mutual trim. So I want to trim those much larger offset surfaces back to each other to form closed manifolds. We've got our hard edges. The red are open surface edges. The black are closed edges. And then I trimmed it to the bottom. So now I've made a little bit of a cutting tool. And I did need to use the surface extend because the untrim wouldn't work here. So I had to add a little bit more material here. I always thought this kind of detail looked like a castle, so I've been calling it the screw castle in my feature tree. I try and do as much as possible of naming descriptive features, or at least putting features into surfaces. So here I just went and I converted the edges of the part into a new sketch and extruded up. And now this is, you can kind of see where this is going. We're going to use the offset surface here to cut away the extra material and provide clearance for the other wall of the part coming in. And then good housekeeping. Models are like campsites. Leave them cleaner when you leave them than when you got there. Use the delete body tool to delete your no longer needed reference or cutting surface. Although some people just hide them, but then in a complicated model, you might have 30 hidden surface bodies at the end. I just like deleting them as I go. One thing I got to be aware of when we're mixing shapes, especially on the outside of a part, no, we want to section this way, that were created with surfaces, and we're now moving into the solid features. So solid features, especially extrudes, everything's always perpendicular to each other unless we've set like a direction vector, something of the like. And because this is kind of a nice arced crown surface, when we pick this inside edge, what do we get here? This is zero thickness geometry because we're zero thickness all the way through this edge. So when I went to combine, it would give me an error. So I use the move face tool. So I just picked all of the kind of perimeter edges of this part, added a 0.5 millimeter, and now everything kind of fully pierces within each other. You can see zoomed in, no longer have that zero thickness geometry error that was up there. And when it comes to merge these two bodies, we won't run into any issues. So just something to be aware of when you're mixing solids and surfaces, that solids like to be straight or revolved, but surfaces can be all over the place. So just zero thickness geometry, be aware of it. If you see that zero thickness error, check along the faces of the parts that are intersecting and maybe add a move face to them. I've also seen combine, which we use to put them together, fail sometimes when surfaces are line to line with each other. So if I'd done a zero offset, replace face, for example, try and just have everything pierce in a little bit by 0.5 millimeter, a millimeter, 20, 40 thousandths, and you'll be A-okay. So now it's really simple for me to use the solid modeling tools to add some additional cuts and such features on this, adding the draft to this part. And so I'm building the outside faces of it. There's some additional detailing that needs to happen over here. So cutting parts before the shell. So you can use the shell to actually cut parts, believe it or not, which we're going to use to hollow this guy out. So if I were to cut use a through-all extrude or something, it would obviously blow through the other wall of the part, which we don't have. But if you just set a distance that's more than the shell thickness, when you go to shell, you just pick those faces. You say, nope, all these faces are going away from the model. I don't want you anymore. I use a little slightly thinner wall section here just to save a bit of material. And now the part's shelled out. I've got my uniform wall. And I can use the combine tool to put it back together. So I added my two bodies, and now I can go through and start drafting. I'm using a little bit of a tricky draft in this situation. So you're looking at this part from the front plane. This part is being pulled via the right plane here. Right, so mold's opening this way. But I need to have draft on this edge. But if I were to add say a neutral plane draft, this edge, well, let's just demonstrate. We'll neutral plane, say a 0.5 degree. Make sure we're going the right way. Arrow, nope, we're going to go the other way. So now when the other part comes in here, unless we angle the bottom face of the other part, it's not going to line up, right? Because this face is now at a 0.5 degree. So to work around that, when cosmetic edges need to be straight for design intent or industrial design intent purposes, what we can do is use parting line draft and draft from the edge that you want to be visually straight, and you need to pick the entire chain of edges. And this draft will build. It may not build at, say, 5 degrees, but at a 0.5 degree, never really run into situations where it fails. Where it fails is if you forget to pick all of the edges. And a lot of the time, you got to manually go in and say, nope, other face. I kind of like doing this one by one so I know which edge is which instead of using the easier option to right-click, select tangency. And now I can pick all of the edges in my chain and actually draft from the edge. And you'll see in order to make this work behind the scenes, SolidWorks is applying the edge from that draft, and here is where we're actually getting the draft built in. So this edge is now kicking up significantly, but I have half degree, and I'll prove it to you with draft analysis. So you can always draft a long chain of edges at a low degree, a half, 1 degree, if you pick the entire perimeter of edges. And now I've added much more material here as this edge kicks up, but I've got a clean half degree through there, and I'm going to have a nice straight edge when the opposite half of this part's not going to look like that. We're going to be nice and straight through here, and you can see that extra material that was added. So you can always draft an entire perimeter. If the feature fails, just go back, look at your little yellow arrows, make sure that they're pointing in the right direction, selecting the right face, and that you've picked the entire chain. So I can always add additional shell geometry. I'm a huge fan of the shell tool for quickly creating geometry. We'll see that in a second. If you do need to create little offsets so that way parts can nestle within each other, the surface offset untrim and then trim to your cutting surface is a great technique. Be aware of zero thickness errors when we get the mingling of solids and surfaces. Just make sure that we don't have those line-to-line edges. We can use shell to actually cut our model and remove the faces. And then we use combine to put it all back together. I want to quickly touch on two strategies for verifying shutoffs. So these little battery retention hooks here are formed by passing steel from the core and the cavity. We all know what shutoffs are, 3 to 5 degrees of draft to minimize the tool wear. Nice little graphic I swiped from the internet. So here you can see, for those of you maybe not so familiar with the shutoff, if I had designed this tab like this, the red section is undercut and would have needed a lifter or a slide or some other translating portion of the tool to allow for proper ejection. Here I have the underside of the hook formed by the core and the top side being formed by the cavity. But I don't actually really have a surface between here to verify that I have 3 to 5 degrees of draft. So one way to check that out, actually two quick ways. When you don't have a face and you want to verify that the steel condition is good, but you don't have a corresponding face in the plastic, two ways of doing that. So here actually, because of the tricky parting line on this, I had to do it a couple different ways. The first way of doing it is our friend 3D sketch. So what I've done here is I converted all of the edges that are being formed by passing steel into my 3D sketch. And you can actually extrude both a solid and a surface in a 3D sketch. You just need to pick a direction. And here, the pull direction is always going to be our direction. And then I just set 5 degrees to verify the shutoff. And now I can look through and I'm like, okay, got plenty of room, so that way the tool maker can build a nice, good shutoff in that area. Another trick, if you want to know exactly what draft angle you have between two imaginary faces, just for the steel condition, is I just do a quick surface loft. So I just pick an edge, pick another edge, and now I can turn on the draft analysis. Oh, hadn't drafted this yet. I guess, oh, right plane, that's why. There's no way this is going to pull from the tool. That looks better. And then I just have this transparent right now. Oh, it's hidden. So we'll show that, and I mouse over. I've got 9.6 degrees on this. So if you're a part designer, just be cognizant. Remember that you're not designing the tool. Like, I'm not a tool designer, so I'm not going to speak to that. But I at least try and give them good geometry so they can make a nice, well-wearing tool. And this is just a quick little check you can do as a part designer to verify what the steel condition looks like. And if you're just new to plastic parts, it took me a couple years, but I was able to eventually see the steel as I modeled the plastic. And if you always think about what the steel looks like, the steel is what's ultimately generating the plastic. So if you're stuck on a tricky plastic modeling, just try and visualize what the negative is. What does all of this detail look like cut into the steel of the tool? And that might give you some clues as to what the plastic geometry you're modeling actually needs to look like. So two ways: you can use a little surface loft trick just to get an imaginary face there for draft checking, or you can use the draft outward here to verify you have enough room in this little cutout for the passing steel. Want to take a look at some undercut geometry and some little tricky stuff that tool makers probably don't like. Well, they like because it adds complexity. Tool cost does go up, but as a part designer, you get a couple more things you can do to leverage cool geometry. We'll jump into SolidWorks, take an undercut analysis pass in a second, but here are 3 kind of common uses of undercut geometry I employ when modeling plastic parts, especially if your customer is really particular about sink on their parts. So this first undercut here, where this really tall rib comes in, there's a screw passing into a piece of sheet metal. So what we did was this rib would have gotten really thick down here and would have probably sunk out. So we just added another rib that's thin, and now this is undercut, so the lifter comes out, forms all this, but we don't have a thick rib that hits the main wall of the part, eliminating sink. I've heard these referred to as dog houses before, so that's what I've been calling them, and this is the dog house undercut. The boss we needed here, I think this was an M8 or something. The insert was massive and called for this really, really thick wall section in the boss. Definitely would have caused sink on the cosmetic face. So we just put it on this little undercut doghouse detail. The lifter slides out, the part can eject, but now we don't have a thick section of the boss at our wall. So if you're willing to pay for the extra tooling complexity of having a whole bunch of lifters, I know this is employed a whole bunch in automotive. I was at a trade show and saw a Ford interior panel. It was a 4-cavity tool with each cavity having 14 actuating lifters to form these. Yeah. So they're willing to pay for it, but just something to consider if aesthetic concerns are paramount, you want to limit sink, consider employing some undercut geometry. And here, this is a functional undercut. I call it functional because there's a little snap engaging in this hole on the part. And leveraging shell for these undercuts. I know I'm going to bring back shell again. Shell, I think, is underrated. It's, you always see one shell in a plastic part to actually hollow the whole thing out. But I like shell just because it's really, really easy to create geometry like this. And I'm going to, like I said before, I'm lazy and trying to limit my picks and clicks. So here I've used a single up-to-body extrude to generate 3 of these flanges, these undercut flanges that'll have a little grommet going in here that will be used to attach these parts together. And this is just a single sketch on our plane. We're going our up-to-body like I like to use. So I now have 3 separate bodies, and now I can go in and shell them. And so now I remove all the other stuff. If I had created this in another way, I would have needed to set up maybe a reference sketch to get this angle because it's not vertical. Then I would need to set up a sketch here, and a plane here, and then 1 sketch, 2 sketch, 3 sketch, 3 extrudes. So just be thinking of how much you can get with a shell when modeling mounting details and such in your part. Here I'm getting all of this extra geometry by using the shell to remove it. The only downside is that you can only shell 1 body at a time, so I have 3 shell features. My little grommet holes, here's my trick of using move face. There's no offset from body option, which would be wonderful, maybe enhancement request for future SolidWorks. So to prevent that line-to-line issue, giving me combine errors, I moved the inside faces in a little bit, combined them together. And one thing I did have to do here was draft them separately because the outside walls are formed by the core, but the inside are for the lifter. So I added draft in 2 different directions, thus a couple different draft features. So you can use shell in a lot of situations. It's a great, powerful tool, and it saves a whole bunch of setup work potentially. Like I said, 1 sketch on this plane, extruded down, 3 shells, which was just picking some faces, and a combine, and I got all this geometry. Probably took me less than 10 minutes to model all of that. So that's just leveraging our shell feature. Also great for doing these little undercut dog houses. Just model the dog house as a box, shell it out, pick the 1 face that the lifter's translating through. And you can also use that multi-thickness. So here I have the ribs interfacing the main wall at 50% of the nominal wall for good rib design. But then I thickened up this face to help material flow into this really thick, heavy boss here. So shell is great for doing lots of undercut type geometry. model it out, and then use the shell to give an opening for the lifter to form the undercut. Advanced drafting. So we took a look at this draft before, but I want to touch on a couple different techniques for adding kind of weird draft to maintain visual styling of parts. So here, this was a circular part, and this outside lip needed to be textured. Let's sketch where we want. Circular draft. Okay. So I couldn't actually use a revolve here, so similar to what I had shown in my correcting draft example, I had to use a boundary surface and not a revolve to create this. So here you can see we just go to our side plane, we've got our angled reference faces, and then I create a boundary surface between them, which approximates my revolve. And there's my little cleanup work. But I'm using the draft tool, so now I need to draft this little lip here, and I need to get 3 degrees on it. So if I were to draft it with a neutral plane like I'd seen before, this edge would go out here, and that might be an exaggeration, but this is mating up with another part, and I want to maintain this clean edge so the parts look like they've aligned in the correct direction. So let's try that parting line draft trick. We're going to go front plane, we're going to draft. So before, I actually want to have 3 degrees on this. I'm going to pick this, I need to go the other way. Actually, let's go 5 degrees of draft on this face. And the feature doesn't build, but it probably does build at 1. But see there, it built. I really need 5 degrees of draft. So what's happening here is that SolidWorks is trying to figure out that weird extension of this edge, because behind the scenes, all draft is a ruled surface. So if you ever want to visualize what the draft tool is doing, just create a ruled surface, one of the surfacing tools from an edge, and that'll show you what the draft is actually doing in the background. But if I were to shorten this edge a little bit, SolidWorks would have a better idea of how to extend this back at this chosen draft angle to get the ultimate shape of this final face when drafting from this circular edge. So how do I get the draft shorter? Here, well, actually I'll show you because I've already modeled it. I'm using a split line. And what split line allows me to do is I can split this big face, right? And now this edge is going to magically become shorter depending on where this split line is. The way I set this feature up is I just start with a sketch, and then I usually, I go more than I think it should. So here, let's go 10 millimeters, and we're going to add our parting line draft at the 5 degrees. It's coming this way out of the tool. We're drafting from our cosmetic edge, keeping it straight. And now SolidWorks is able to figure out that extension. And what I'll do to make this extension a little bit smaller is start just inching this guy back. Rebuild, okay. Maybe let's try 6. 6, the feature fails. So I'll try and just shimmy up to it as close as I can, maybe 6.5. 6.5 didn't quite work. And the higher the draft angle, the more this distance needs to be. So let's just go back to our 8 millimeters. And now the draft feature works. So it's kind of just a little bit of guess and check to dial it in. But now if we were to view from this orientation, we have a nice, clean, straight cosmetic edge. And we can actually bury this increase or this extra geometry in the lip and groove detail between these two parts. So you can always do that sneaky kind of draft from a circular edge. You may just need to shorten up the edges. One last little cleanup thing I like to do is delete face. Powerful tool. That split line we had in there, we'll just pick those 2 new faces and we'll delete and patch. Oh, didn't like that. Might be able to get these. There we go. And so split line feature is out. I don't have that extra edge, but I do have the draft. So split line is a great tool for artificially shortening an edge, so it's a little bit shorter when wanting to apply the draft feature to get tricky, complicated drafts to work, but your parts look pretty with nice straight edges on the outside. And here's that parting line draft. You can always draft a whole series of edges. This part was being pulled perpendicular to this. So we're looking directly into the direction of pull, so I needed to, the mating part was opposite of that, So to get everything lined up, we needed a draft from that whole chain of edges to keep a nice, straight visual line on the outside of the part. And here, this one was tricky because look at all these edges, and that's why I like picking them one by one by one, so that way I can correct the other face with the yellow arrow is pointing in the wrong direction. One last little advanced drafting thing is jogged parting lines. So here we had done the part, and the toolmaker came back to us and said, hey, we actually want the parting line to kind of come across like this. These ribs are really tall, and they're on the cavity side. We're concerned of it sticking, the amount of ejection force we need. So we said, oh, well, we can change that. But now we need to go back and actually jog this parting line versus on this geometry which had already been created. And it's actually really easy to do if you use this one trick. You can do this with a cut, but this is not going to be with a cut. This is parting line. Perfect. So here, my folder, I want to go back. I know it's this feature right here. So let's roll back a little bit. Note that a lot of these parts I've just kind of cut away so that way you can't see the whole thing, so you won't kind of guess what it's from. Doesn't really matter. It's just the fact it's a plastic part. So we're adding draft, and then my next thing I'm going to do is I want to jog the parting line. Let's turn on draft analysis so we can see where the core cavity split is and the parting line is. And we'll just go a ½ degree. See, originally the parting line was down at this edge. We want to move it over and kind of jog it. So I've started a new sketch or a new plane. I just used this as a reference and the right plane so I could create plane because I didn't want to sketch on the already drafted face. And so I've sketched what I want my parting line to be. I have 5 degrees here because there's actually going to be a new face generated by this technique that will be the shutoff between or as we jog this parting line. So I have my sketch, and note the sketch doesn't get absorbed. I use the split tool. So what split does is split bodies in half, or not in half, but in any combination. You can use sketches, planes, surfaces to sketch or to split. So I have my trim tool. I hit cut part. And then I just need to click one of the bodies. It doesn't matter which one. If you don't have anything selected, the split won't work. And so what I've actually done is, if I were to say isolate this, I've cut the part in 2 pieces. And if I just use the split line, you said, well, why didn't you use a split line there to add the draft, and then the draft, and then split line, and then add the draft to these faces? It wouldn't build. I need this one extra face, and I get the shutoff face for free. So now, when I isolate this body, I have a new face in my model right here. This face did not exist before the split. And draft can't generate new faces, but what it can do is just work on existing ones. So by splitting it at that 5 degrees, this is a new face introduced by the split, which allows me to add the new jogged parting line draft from here, and I've got my shutoff. So I was really easily able to jog my parting line. Just remember that split. If you ever need to do any kind of parting line, or you've got a little tab that the parting line wants to jog down to build that tab, split it along the intended parting line, add the draft, put it back together, and combine. Split's useful for a bunch of other things. Stopping fillets early. Just split the draft, or split the part wherever you want the fillet to end, add the fillet, combine it back together. It's useful for diagnosing geometry errors. You have a draft that won't build. Cut away a portion of the part so that way the solution is easier for SolidWorks. I've had complicated lip and groove drafts that wouldn't build in one feature. Cut the part somewhere along that lip and groove, draft them individually. It both built, and I was able to combine them back together. So here's that jog parting line. Make sure that in your sketch you've got the 3 to 5 degrees for the shutoff on the newly generated face. And here's that new face generated by the split, which will act as our shutoff face. And we're going to put them back together. And the last thing I want to leave you guys with is an example to easily do ribs on curved surfaces. And you will not have to create a whole bunch of planes for every one of these ribs and do them as sketch offsets. Ribs on curved surfaces, super simple if the order of operations is followed. So here I've got some little ribs on this part. and we're going to take a look at how they were done. Once again, I put the ribs into a folder. Just wait for SolidWorks to rebuild for a second. The first thing I want to do, just similar to the non-planar lip and groove example, is I'm going to, before any of the ribs are built, I'm going to offset the inside faces of my part, the rib height. So now I have a new top surface for my ribs, and I'm going to create, here, looks like I just had some setup work. And here I'm using a thin feature extrude. So I can extrude all of this. I couldn't use the rib tool here because the part is not mirrored yet, and the rib tool always needs a bounding to end. So that's why I'm using the thin feature extrude. And now I can extrude this, not merging it, up to body. So my ribs are actually going to stop at the main body, but I haven't controlled the top of them. But because I haven't merged it, I don't need to worry about this surface trying to cut any of this other geometry in the part. I am only concerned about it cutting my ribs, which are living as a separate body. Use a ruled surface with the sweep option just to have a nice clean transition instead of using extend or something. I could have extended, but I was kind of concerned about how pointy these ribs were getting. So I just needed to make sure that my cutting surface was larger than the ribs. I'm using the knit tool. Knit tool puts two surfaces together. So that black edge means that these are joined. Red edge, normally blue. I just like red open surface edges. Just my system setting. Knit together, and bam, there's our cut, just like we've seen before. And it's so much easier working in a multi-body environment to cut these ribs because I don't need to worry about this trim surface cutting or interfering with the rest of the part. The final ribs, and if we were to show the part, sometimes you can end up getting a whole bunch of bodies with this, but that doesn't really bother me because it's such a quick way of doing them. I used a move face just to cut that down a little bit. It was too tall. It was interfering with the lifter, I think, forming this little snap hook. And combine, I don't even need to pick the individual bodies because I got a lot of them, and that's picks and clicks I won't want to do. Just window select everything, click OK, and bam, all your ribs are joined into the part. So I use this technique all the time for creating ribs on curved surfaces. The only downside is you got to come in and use parting line draft on all of your edges. It's just when you start getting into advanced stuff that saves you time, it's just there's a lot of picks and clicks for doing these funky kind of ribs. So it's just going in and picking them. Maybe get an intern and have him add draft 33 on your part. One thing I want to mention, which is a cool little trick. I kind of wondered what it was at some point, so I'm going to add a 0.5 millimeter fillet at the junction of these ribs just to improve flow. Is this little pop-up, which is actually useful. I didn't know what it does, but it gives you different options of ribs. So sometimes you'll get a good option that works for your rib fillets. Sometimes you won't. But a lot of the time you can get all of the vertical ribs between I keep saying ribs, I mean fillets. I guess I'm hungry, I need to have dinner. Try and add all of these ribs. Try and use fillets, fillets and ribs. This is terrible. Try and add all the fillets to the vertical rib intersections, and then you can come in and you've got tangent paths, so it's much less edges to pick when you go through and add your final ribs or fillets at the bottom of the ribs for flow. So to recap this example, ribs on curved surfaces, just remember your surface offset. Don't merge. Multibodies are your friend because you can do so much more with them. And then cut your ribs to height and come back with the draft tool and then use this nice lifty pop-up. It's an old screenshot from 15 before they made everything blue. And then come back in and there's less edges to fill it because of tangent propagation. So if you like this session, please take a minute and give your thoughts via the SolidWorks 2017 app. Surveys are here. Be happy to take any questions, answer any of your individual questions at the front here. Thank you very much for your time. Please grab a business card with our company website.